Alright, in this video I want to show you something that I think is pretty cool, and that's three things that seem completely unrelated, at least when you first learn about them, and yet there's actually a pretty cool connection between them. So here are the three apparently unrelated things, and then we'll tie them all together. The first thing is something called Pascal's triangle. It's named after a French mathematician and theologian, actually. His name was Blaise Pascal, who I believe lived in the 17th century, if I'm not mistaken. But anyway, he made a number of important contributions to math, and one of the things that he came up with, or at least it's named after him, something called Pascal's triangle. And so here's what that looks like. You start with the number 1, and then our second row of this triangle is going to have 1s in it. And then the outside parts of the triangle are always going to be 1s. Okay, but each time we make the triangle, the inside parts, we just add those together. So 1 plus 1 is 2. Our next row is going to have 1s on the outside, and then we're going to add those together. 1 plus 2 is 3. 2 plus 1 is also 3. So you can see the triangle is growing by one number each row. The outsides are still always going to be 1s. And now we'll add these again. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So you can kind of see what the pattern is. Let's do maybe one or two more rows. So 1 plus 4 is 5. 4 plus 6, 10. 6 plus 4, 10. And 4 plus 1 is 5. And maybe one more. Outsides are still 1. 1 plus 5, 6. 5 plus 10, 15. 10 plus 10, 20. That's going to be 15, and that's going to be 6. Okay, that's Pascal's triangle. That's all very exciting, but we'll bracket that for right now. Okay, second topic, apparently unrelated, at least at the start, but hopefully you'll be able to see pretty quick what happens here. So something called binomial expansion. A binomial is something like this. A binomial is, it has two terms, so like x plus 1 would be a binomial. Let's raise x plus 1 to the 0 power. Anything to the 0 power is equal to 1. Okay, then let's take x plus 1 and let's raise it to the first power. Anything to the first power is equal to itself. And I'm going to write that, even though it's a little stranger, I'm going to write that as 1x plus 1. Obviously 1x is the same as x, but I think in a sec you'll see why I'm writing it that way. X, okay, let's do the second one. So we raise it to the 0 to the first, now we're going to square it. Remember, when you square something, that's like multiplying it by itself. So if you FOIL that out right there, you're going to get x squared, which I'll write as 1x squared, plus you're going to have 1 times x, that's 1x, plus another 1x, that will be 2x, and then 1 times 1 is 1. Okay, let's do a couple more. So that now it starts to get kind of painful, because now you have to cube that, so you have to take the thing that you just had right here. Let me do a different color here. You have to take this thing, and you have to multiply it by yet another x plus 1. Okay, so I'll just save you the time in doing that. You can FOIL it out if you want to, but when you do, you're going to get x cubed, which I'll write as 1x cubed, plus 3x squared plus 3x plus 1. Okay, let's do one more, and again, I'll save you the trouble. This starts to get really messy at this point, because now you have four, not just 3 of those, but 4 of those. It turns out to be x to the 4th plus 4x cubed. I'm actually doing these in my head, and I'm going to show you a shortcut for how to do that in your head in just a sec. You might have already noticed how to do this. Plus 4x plus 1. Okay, and that's a 1x to the 4th. So here is the connection. I told you these things were apparently unrelated, but maybe you can tell me, if you look at it for a sec, the connection between what we just did and Pascal's triangle. Here's the connection. When I raise something to the 0 power, my coefficient is 1. When I raise it to the 1 power, I get two coefficients, 1 and 1. When I raise it to the second power, I get 1, 2, 1, just like the third row of Pascal's triangle. So when I raise it to the 0, I get coefficients which are equal to the first row of Pascal's triangle. When I raise it to the first, I get the second row. When I raise it to the second, I get the third row. So how did I do this big one right here, this messy one? How did I do that so quickly in my head without actually having to FOIL this whole thing out? And the answer is I knew that I was raising to the 4th power, so I knew that I should get 0 power is first row, first power is second row. I knew that the 4th power should be the 5th row in Pascal's triangle, and that is this right here. You can see 1, 4, 6, 4, 1. There's the 1, 4, 6, 4, 1 right there. So what Pascal's triangle tells us is when you expand a binomial, and expanding just means multiplying it, when you expand a binomial, the coefficients in front of the powers are going to be the same as these numbers right here. If you're raising to the 4th power, you get the 5th row. You're raising to the 3rd power, you get the 4th row. In other words, if you're raising to the 2nd power, you end up with 3 terms. And there are 3 terms in the 3rd row. If you raise to the 3rd power, you end up with 4 terms. So the pattern is whatever power you're raising to is 1 greater than that in terms of the number of things you get out, the number of terms. If I were raising to the 100th power, okay, I would end up with 101 terms. That would be the 101st row of Pascal's triangle. Okay, those are the first 2 topics. Third topic, and this is going back to what we talked about in the previous video, combinatorics refers to permutations and combinations. Okay, permutations and combinations. So suppose that you were doing the 100th row. And the question is, well, certainly the most painful way to do it would be this way. X plus 1 times x plus 1 100 times. That would be the worst. Pascal's triangle wouldn't be a whole lot better, though, because Pascal's triangle would require you to follow this pattern all the way down. Notice here we're only at the, what's that, the 7th or the 6th row right there? That's the 6th row, I think, if I count it correctly. So you'd have to draw that out 100 times. Is there a faster and easier way? And the answer is yes. We actually learned about that in the prior video, or roughly. I'm going to show you what the connection is. So the connection is this. These numbers are actually also numbers that you can get from using combinations. So for example, let's just take this one, the 3rd power. Notice I have 4 terms right there. So let me move this over for a sec. So my 4 terms have coefficients of 1, 3, 3, and 1. Those are the 4 terms. So I want to show you how that relates to combinations. If you were to do this, I'm going to rewrite this here. You have 1x cubed plus 3x squared plus 3x plus 1. Okay, I'm raising to the 3rd power. So that came from raising to the 3rd power. This number right here, the 1, that is the same as 3 choose 0. This number right here is the same as 3 choose 1. This number right here is the same as 3 choose 2. And this one is the same as 3 choose 3. And another way that you might see this written in some textbooks is 3 with a 0 on the bottom. That's another way of saying 3 choose 0. Another way of writing that would be 3 choose 1. Another way of writing that would be 3 choose 2. And another way of writing that would be 3 choose 3. So I just want to show you when you put that in a calculator what it looks like. Okay, so we said if you look at those numbers 1, 1, 3, 3, and 1, let's just prove that this equals what we said it should equal. So we'll go to math and then prob, and then we want to do 3 choose 0. This should equal 1, and we can't see it because it's off screen, but you can see it does equal 1. Okay, let's try another one. Let's do 3 choose 1. We said that should equal 3, and it does. Okay, so how would we make that easier if we were doing the 100th row of Pascal's triangle? Let's suppose I wanted to know what's the coefficient. And actually I want to show you one more pattern because this is all about learning the patterns. Notice that my first term is choose 0. My second term is choose 1. My third term, that's this one, my third term is choose 2. Okay, so let's suppose that I was doing the 100th term. Let's suppose I was doing x plus 1 to the 100th power, and I just want to get the first couple of these, okay, the first couple coefficients. So the other pattern to notice is this. If I'm raising something to the 3rd power, it starts at cubed and it starts counting down. X to the 3rd, x to the 2nd, x to the 1st. This last one is like x to the 0. So let's just get the first couple terms of x plus 1 to the 100th without having to draw out all of Pascal's triangle and without having to do this either. Without having to do x plus 1 times x plus 1 100 times. So here's the pattern. Notice that here we were raising to the 3rd term. So we know our first couple are going to be x to the 100th. Then we're going to have x. Let me leave some more space so we can fill in those numbers. Let's get the first 3 terms here. Our next one is going to be x to the 99, and our last one is going to be x to the 98. Now how do we find the coefficients in front of them? Well, this first one will be, and actually I'll write it with the choose notation because that's what you're more used to seeing. This first one is going to be 100 choose 0 because 100 comes from this number, and because I'm finding the first term, remember this pattern up here, first term means you're choosing 0. Second term means you're choosing 1. So that first one's going to be 100 choose 0, then I'm going to have 100 choose 1, and then I'm going to have 100 choose 2. So let's find out what those numbers are. Okay, so 100 choose 0, and I can tell you in fact anything choose 0 is just going to equal 1, so we don't really have to worry about that. So let's change these numbers right here. 100 choose 0 we already know is 1. 100 choose 1 is equal to 100. And then 100 choose 2, it's going to be a larger number. 100 choose 2 is equal to 4,950. So you can see the numbers start to get I'm not going to say random, but they do start to get away from what we're used to. So we just found a much easier way of doing something that could be a very hard problem. So 1 choose 0, that's 1x to the 100th, plus this number turned out to be 100. And by the way, anything choose 1 is just that thing. So a million choose 1 would be a million. A billion choose 1 would be a billion. And then the numbers after that, there's not so much of an easy pattern. That one turned out to be 4950. And obviously it keeps going for 100 terms. But I always found that to be a fascinating connection. You have these three apparently totally unrelated things. You have this, kind of cool looking pattern with a triangle, but what does that have to do with anything? You have binomial expansion, which you're familiar with from using FOIL. And then finally you have this new combination stuff that you just learned. What do those three things have to do with each other? Well, now we know exactly how they're connected.